For the talk titles. It's partly explained by the vacation, I guess. Many people were unable to provide their titles. However, I was told by Frank Kelly that it's very important to have those titles in place. One of the reasons is that these talks get announced around Cambridge and they go to other departments like the Department of Mathematics and so on. And people have no idea what they're going to be listening to unless they have a talk title. So if you're a speaker in this conference, please, as soon as you can, provide your talk title and preferably also an abstract to Heather. Or if you like, you can give it to either me or Francois, and then we can forward it to Heather. The second announcement has to do with the open problems sessions. We have about 4 or 5 interesting open problems, so we can have an interesting session on Tuesday. But we'd like to encourage you to provide more interesting problems so that we can make this a more interactive and hopefully also productive affair. I don't think it doesn't have to be very formal. If you can just sort of think of something that's been on your mind in the recent past that you think you might want to share with us, or perhaps get some insights from the community. You're just writing it out by hand or something, just running it by either me or Francois would be a good idea. And then if we get a few more of those, we'll have a fairly interesting 2 sessions, I think. So our second speaker today is Muriel Medard, and there's the title, Some Newish Results in Networking.
Thank you, and thank you to Francois and to Kat for inviting me. So I think usually one more formally starts, can everybody hear me? I'm using my teaching voice. So more formally one usually puts recent, but this is a combination of some things which are very new and some things which are less new. But my hope is to bring them together. Can you hear me? Oh. Can you hear me? Thank you. But to bring them together in a way that is pointing to new directions. I'm not going to do a good job at saying who did what, who contributed what. These are my main contributors. Foremost among them, of course, is the late Ralph. And really, I think the bulk of the insights I hope I share today really comes from many years of working together, and he really should be the one giving this talk. So anyway, I'm going to give some overview, some new results in information theory, and the main thrust of the main topic of the talk is that really many of the recent results and many of the places where we have had considerable success, particularly using random approaches, have been because we've been considering multicast. And by multicast, I mean a system in which all of the receivers want everything that is sent. And I'm going to go a little bit in detail over this. I'm going to talk in particular starting from the network coding, starting from the algebraic model for network coding. I'm going to sort of develop a bit the whole range of different multicast results that are out there. I'm going to in particular cover random codes in order to build multicast. This is going to be sort of a very important, really sort of like I said, the main premise of my talk, that random codes do very well in multicast settings. And I'm going to try to illustrate that by generalizing the kinds of networks we consider, going beyond just error-free networks, which the original algebraic model envisaged, and considering networks with erasures, errors, and so on. And then talk a little bit about some recent results in HSNR by David and others. And then I'm going to move away from that and say, well, what happens when I don't have multicast? Which of course is the case in many of the interesting networks. And then we'll sort of revisit the algebraic model to say, well, roughly things are ugly. But even though things are ugly, it doesn't mean that we no longer have any use for random approaches such as we had in multicast. It just means that where they fit is maybe somewhat different than where they used to fit. And maybe all that we can hope for is to have equivalence among ugly things. So just to have one ugly thing which is as ugly as something else. So let me start out here with just a very general network system, but actually very idealized. So this is starting out with a network without noise. And what do we usually talk about when we think of a network without noise? Capacitated, of course. I'll have certain sources. Of course, I have a network. I have vertices. I'm going to look here at just point-to-point links, edges. And I'm going to have capacitated edges. And I'm going to have some sources. and I'm going to have some sinks, and presumably the sources want to connect to the sinks. That's the whole point of having the network. Okay. And what do I mean by communicating? It means that I'm going to have a set of random processes which are available at the sources, and a set of random processes which are available at the destinations. And I've managed to set up a connection if I have a triple of a source, a destination, and a set, I'm going to call it cal x, of random processes, such that I am able to observe this set of random processes at the receiver. So cal z is the set of random processes that a receiver sees. Cal x is the set of random processes at a source. If I'm able to reconstruct at the receiver a certain set of random processes. So these are the random processes that want to go from V to U, and I've managed to set up the connection if among these random processes that are going from V, this random process going from V to U, are part of the random processes that are available to me at the receiver, right? So I have something random at the source, was I able to reconstruct it at the receiver? That's basically what this says, right? And so really when I'm asking in a general way if I was able to set up a connection, a set of connections that I call cal C, it means give me the network, give me the set of connections, that's to say really the set of demands, okay? And the network coding problem is, given this network and given these connections, can I do it? Okay, so this is sort of the first problem, is really just a feasibility problem. Okay, yes?
I'm a bit confused by nothing.
Yes?
So you want xvu to be a subset of xv.
Right,
So
because...
what about the part of xv that's not in xvu somehow?
So the source may be wanting to connect to other people,
Okay.
right? So a source may
So
have...
the union of all these xvu somehow should be thought of as xv.
That's correct. That's correct. Right? So you have a bunch of random processes at a source, some of them which are destined for you, some of them are destined for some, and some of them may be destined, of course, there's intersection, right? So some sources, a single source may have things that are destined to more than one place, right? So it's not uniquely multicast, it's not uniquely point-to-point, it's just, you know, so that's exactly it, okay? All right? Okay, so the first question, of course, is the problem solvable? Can I actually fit in these connections into the network? And of course, the attendant question is, can I find a solution? It's nice to know that it's solvable, but very often, you know, we'd actually like to find out how I can find a solution. So of course, this is extremely idealized, right? There's no synchronization, there's no protocol, there's no noises, there's no errors, there's nothing right now, okay? But it will build up the complexity and the deleterious effects from the network gradually to see where this goes.
What does solution mean here?
So how a solution is, we'll see that in a minute. It's actually how, so is the problem solvable? First of all, is it doable? And if so, what does the network have to do? What do the nodes have to do in order to achieve this observability of processes at the receivers from the sources? Okay? Okay, so I'm going to start out assuming that, and this goes back actually to the questions. That was a perfect segue. I'm going to assume here, to start out with, that my codes are linear. What I mean by my codes being linear is that if I look at any particular node in the network, it's going to have these sources here. It's going to have some exogenous inputs, that's to say things that are joining the network at this node. There may be none. For instance, an interior node is just not going to have anything. And it's going to have some endogenous inputs. So endogenous means that it's getting stuff from other edges inside the network. And on any edge coming out of a node, I'm going to do a mixture, which is linear, and in this case it's scalar. We'll talk about non-scalar a little later, but let's just stick with scalar here. It's going to be a scalar mixture of endogenous inputs and exogenous inputs, and that's what it's going to plop out on its different edges. Okay? And you can see how you could generalize this. Of course, I'm thinking of a graph here, but you can generalize this for a hypergraph, particularly for wireless, where you may have several receivers getting several nodes getting the same thing. You can generalize this to a hyperedge. Okay, so I'll talk about edges and graphs right now, but you know, hyperedges are very similar. Okay, so that's what the network does. And then if everything that the network does is linear, then if it can be undone at the receiver, it can be undone linearly. Right? That is to say that when we go and see the observable processes at each of the receivers, if it can be undone, then it means that if this is a terminal node, a receiver, it has to be able to take some combination of all endogenous inputs, okay, and pop up a Z, where remember the Z's are the processes that a receiver sees. It has to be able to go ahead and produce a Z, which is going to be of the right set, right? So the kinds of Z's that we wanted to observe, right? So if we restrict ourselves to linear codes, that's really what we would like to do. Okay, so fair enough. That's what the network is doing. So now, if we want to look as to whether there is a solution, we would try to see how am I going to look for these types of coefficients. The alpha coefficients here, if you will, are the coding in at the ingress of the network, right? This is the exogenous input, so you can think of these as the precodes. These are the codes in the interior of the network, and my epsilons here are the decoding coefficients. Okay, those are the decoding coefficients. All right, so I'm going to have a bunch of inputs. I'm going to have a bunch of outputs. I have an input vector, which are the processes that are being placed into the network exogenously, right? Of course, they can come in at any point. I'm just sort of showing them all coming in at the left. And I have my output vector, which are the processes that are coming out of my network, okay? And everything inside my network is linear. I'm going to have the pre-coding, the coding inside the network, and the decoding. And I'm going to combine all that into some matrix M. Okay, since everything that I've done is linear, I have a linear system where I have X coming in, Z going out, right? Of course, this could be at, some of the nodes may be the same, and which is coming in and going out. And I'm going to have a matrix M whose coefficients are just these linear coefficients of what's going on in the network. Okay, so it's just a linear system at this point. Okay, so how can I figure this out? So, all right, you say, all right, it's a linear system, but in general, my network may be quite a mess. And how on earth am I going to look at my network and figure out what this linear system is, right? Because there are all kinds of paths I could be taking through my network. Am I going to have to enumerate each and every path, look at all the possible combinations, and have some sort of massive exploration of what this matrix is? Okay, so at this point, it's like, okay, fair enough, everything's linear, the whole system is linear, but how do I actually apply this to a network? Well, it turns out that it's not that bad, and let me just give you a little idea here. So let me look at this little network here. So I have two input processes and two output processes. I have one sender, one receiver, right? That's not important. I mean, it's just because it's a small network. And if I were to look at this network, and if I were to look at an edge incidence graph of this network, I would say, well, edge 1 is incident upon edge 3. So there's a contribution, a linear contribution of edge 1 onto edge 3, which I denote here by beta sub E1, E3. Edge 1 is incident upon edge 4, which I denote here by this beta E1, E4. And then, of course, E3 is incident upon E5, and E2 is incident upon E5, and that's it. Right? That's all I have. So the only places where I can try to choose coefficients are these, right? So for instance, E1 is not incident upon E5, right? So I don't have anything in that location. So it's an edge incidence matrix, but instead of having zeros and ones, I've replaced the ones with just some free variables that I get to pick. Okay? Now, if I look at what's going on in the network in terms of setting up connections, this is, this gives me my little edge incidence matrix. What I'm doing in the network is I'm stepping from one edge to the other, right? Not necessarily in a path, but every time that I go one more step in the network, I'm really applying this matrix F.
Your network is a DAG.
Pardon? In this case, it is a DAG. I'll talk later about, that's a very good point. And I'll talk later about what happens with cycles. With cycles, you have to have delays, right? Because otherwise things rapidly go wrong. So it turns out I don't have any slides on it, but it turns out if you do have cycles, then of course you have to have a delay. You have the same thing, except you'll have a polynomial in D, right? So then basically what will happen is you're building a convolutional code. But the similar approaches hold. Okay? So then what happens here is I'm going to be summing up the path gain, so I can apply it up to a certain number of times. So basically I can take this middle part of what's going on in the network, the actual code inside the network, not the decoding part or the pre-coding part, and I can express it this way, right? And it's just built the point is that it's built mechanistically and automatically from the edge incidence matrix. Yes?
But without a cycle in the DAG, as Frank had,
Yeah.
there may be no need to sum it over to infinity, right?
Pardon?
Maybe only
Well, but eventually, I mean, this will only have so many terms, right?
I see.
Eventually you fall off a cliff,
Okay.
right?
Quite a few.
Yeah. Okay. Sorry. There was.
No.
Oh, okay. All right. So with what happens with the cycle is you get polynomials in D. But by the way, everything holds with the cycles. But of course, you need to have a delay, so you need to do all these things over polynomials in D, because otherwise, causality wouldn't hold and life would not be good and things like that. All right. Okay. So what do I have? I have an input X. I have an output M. I have an output Z. It's related by this matrix M, which is the in toto effect of the network. If you recall, the pre-coding, the decoding, and the stuff in the middle, which we just talked about how to get, okay? And now, if I'm trying to figure out how do I recover the receivers, the right stuff, how does Z map properly onto X, I'm really looking at polynomial functions in variables xi, where xi is are variables which include the pre-coding, alpha, the decoding epsilon, and the coding inside the network beta. Okay, so now I can look at these xi's, and what it gives me is first of all, a very cute algebraic version of the min-cut max flow. Okay, and the version of the following. So suppose I have a point-to-point connection. Okay, so at single sender, single receiver. Then we know that that connection is possible if and only if the min-cut max flow holds. Right now, I've assumed that all the sources are independent. I forgot to say that, but I'll relax that later. All the sources are independent, and basically, let's assume each source has a rate of 1. So the rate of a connection is just the cardinality of the set of connections I want, right? I mean, you can always, modulo issues of integrality. I mean, this is very straightforward, and you can show that it's the same thing for me to have this as it is to say that the determinant of the transfer matrix M is non-zero. That is to say, I can select these xi's to be so that the total determinant is non-zero.
Could you go back one slide, please, with the definition of M?
M is the whole transfer matrix.
But it doesn't have a xi in it. So.
The xi's, yeah, these are the xi's.
Oh.
The weights.
Yes, they're the weights. They're the weights that include, exactly, yes, thank you, John. It's the weights that include the internal, the pre-coding, and the decoding. Okay? So these are the xi's. Okay? All right. So now, basically, for me to be able to set up these connections, right, I need to be able to have this, to have the determinant of this matrix, which is a polynomial and multinomial with xi's, be non-zero. Okay? That's all I need. And if I just have a point-to-point, I can actually just have binary codes, right? We know that. Basically, we don't need to code if I only have point-to-point, right? I knew that I didn't need to code because I had the min-cut max flow already hold. Okay. Now, what happens if I generalize this, instead of having a single source, a single receiver, let me go to a single source and multiple receivers, all of which want the same thing. So the reason why now putting this thing up in matrices is nice is because you can start doing proofs basically just by staring, right? And a few color crayons. Okay. So let me me look here at this multicast network. So I have a set of inputs, I have a set of outputs. Okay? Remember, A is my pre-coding for my inputs. In the middle is some mess, who knows what it is, but I know how to characterize it just from the edge incidence matrix. Okay? And then I have a decoding here at the end, a matrix B. And what am I saying here? Well, this receiver, the blue receiver up here, can only decode using the stuff that he sees, right? He cannot collaborate with the other receivers. He's as though he was by himself. As far as he's concerned, right, he needs to be able to recover stuff just like in the point-to-point. He doesn't get to cooperate with the other receivers. This receiver also has to do things by himself, and so does this receiver. So if I look at the entire effect, right, I'm mapping a set, I'm calling K here, K here is the number of receivers. I'm mapping onto the cardinality of CalX, which is the number of input processes, onto K times the cardinality of CalX, right, because it's CalX cardinality for each of the receivers, and I have K of them, right? So in this case, this is a 3, so K is 3, and cardinality of CalX is 3, so it would be a 3, this would be 3 rows, 9 columns, okay? And now each of these matrices, by the same theorem as before, has to be invertible, right? So this is what happens now. Each of these matrices has to be invertible. If one of them is not invertible, I can't set up the multicast. So what does this say? It means that the min-cut max flow, which of course was necessary for multicast connections, is not just necessary, but is also sufficient. The only little difference maybe now, that I may have to go up in field size or, at least get a longer vector, because when I look at this polynomial for each and every one of these different matrices, I have to make sure that not only do I not step on a root of this matrix, of the determinant of this matrix, but that I also don't step on a root of the neighboring matrices. So the field size is going to grow at most, of course, with the number of receivers, with K. Okay, so that's basically it. So now my problem is, I look at this matrix, the determinant is going to have some roots. I should just avoid stepping on the roots. So it's a problem on not stepping on roots. That's it. That's what I'm really trying to do with the multicast. So if I'm going to really put this in terms of a theorem, it's basically exactly what I just said. So there's going to be existing a linear network coding solution. And again, it's just by staring at it. Each of these matrices, these different colored matrices, the yellow, the blue, and the red, is exactly what I had before in the single point-to-point case. Okay? So we're able to recover the min-cut max flow theorem for multicast network coding of Alsved et al., where it says that the min-cut max flow condition is not only necessary, which of course it always was, but also sufficient, which is of course not the case when we try to do it by routing using trees. So now you say, okay, well that's kind of cute, right? I mean, you can do it algebraically. Now you have sort of an algebraic characterization of min-cut max flow. What do I care? Okay? Well, there are a couple of reasons why you care, or at least why I care. I hope you all care too. First of all, is now you can start proving somewhat different theorems, okay? So you can not just do multicast, but you can do sort of son of multicast, all right? So let me give you a little example here. I have a single source, and I have some receivers that want everything, and then I have a set of receivers which want disjoint sets of everything. Okay, so you can just look at the matrix shape here to see who gets what, right? So this guy just wants the red, this guy wants the yellow, this one guy wants the blue, and these two guys want everything. They're denoted in black. Same thing, right? As long as the min-cut holds for this ensemble of colored receivers, and as long as the min-cut holds individually also for the black receivers, everything holds. Right? So you can do certain things. You can also do a two-level multicast and so on. Yes?
Sorry, I'm a little bit confused by this picture.
Yes?
So does this contain as a special case degraded message set where some nodes want a subset of everything.
But the subsets have to be non-overlapping. The subsets are overlapping, we'll see later, all hell breaks loose.
So I cannot have all users want the whole, 5 receivers all want the whole thing.
That's fine. If 5
Three of the
receivers want everything, then I'm back here.
And 3 receivers want something additional beyond that whole thing, for example. That's no good.
No, that doesn't work. Okay, so let me give you a sneak preview of where,
So I didn't quite understand what does the message structure here correspond to?
the message structure corresponds to some receivers want everything,
Okay.
and then there's a set of receivers such that they want disjoint portions of that, but collectively they want everything.
You start from the bottom up, maybe that's an easier way to do it.
Pardon?
You have some groups and then you can
Exactly.
those groups.
Yeah, maybe that's right. So whichever way, but that's the structure, right? So in effect is, I have a bunch of square matrices, right? And this is a square matrix. Also, I just changed it a little bit, right? Of course, by the way, for the multicast, it doesn't matter if I have a single source or multiple sources, right? It's quite clear here. It wouldn't matter if I had a single source or multiple sources, right? Just think of either putting a super source, but the structure doesn't change. So all these things flow properly. Okay? So basically, I get not just the multicast, but I get things that are multicast-like, where everybody wants the same thing, or it's almost as though everybody wanted the same thing, right? You see, this is not something where everybody wants the same thing, but it's analogous in structure to the multicast. Okay. So now, let me go back to the multicast. What's the second reason why I care about having a nice algebraic setup for this? So remember that I mentioned that really all I need to do for each of these submatrices is to avoid roots. Okay? So how do I avoid roots? Well, I can either be very clever and look at the roots instead of try to avoid them, right? So I can do it in a deterministic way. Or I can say, oh, what the heck, just go over a large enough field size and how likely am I to step on a root, okay? And of course, that's, a more formal way of saying that is that we choose them in a distributed random way, okay? And the probability, of course, of stepping on a root goes down exponentially with the number of bits in your code, right? And so it's really very similar to Schwartz-Zippel. And actually, it turns out you can get a bound which is a little tighter than what you would expect with Schwartz-Zippel. Schwartz-Zippel you often use for things like, doing randomized, bipartite matching. And actually, it turns out that if you play with this, you get an Edmonds matrix. You can reduce this to an Edmonds matrix, and then you apply Schwartz-Zippel on that successively through the network. And you can get a fairly tight bound, which depends on the maximum in degree of the nodes and stuff like that. Okay? But basically, the main point is, because we had multicast, I can build my code in a completely distributed manner. Right? So it's really because I looked at those matrices, and I looked at the structure of those matrices, that I can build my code in a completely distributed manner, randomly over a large enough field. And I know how quickly the probability of error, which is the probability of choosing the code incorrectly, goes down. Okay? So I have a random and distributed choice of coefficients, followed, of course, at the receiver by matrix inversion. Okay, so I know the complexity of undoing this. This may not be the happiest complexity, but it's okay, right? Now, let me remember that I said I was going to start gradually making that very simple model a little bit more complicated. Right? So I had no erasures, no errors, the delays, as I mentioned, that's not an issue. You build a convolutional code. Let me start by relaxing the independence. Okay, so I'm going to take out the independence. So what does it mean to take out the independence of the sources? Well, let's go back and think when we usually look in information theory at dependent sources. Well, of course, exhibit A is the Slepian-Wolf theorem. Right? So if I look at the Slepian-Wolf theorem, I have two sources, and their dependence is such that the conditional entropy of the second given the one may not be equal to h of x2. Yes?
Actually, what do you mean by independence? Everything you did up to this point is deterministic.
Everything was deterministic, but you see, when I was doing, everything that is deterministic, but when I was doing this, inversion here, you see that if the axis, for instance, right, had a dependence, say linear dependence, right, there would have been an extra thing here. So here I assume that I had to have inversion. And that had to be invertible, right, right. But if the axes were dependent in some way, right, then maybe I could have gotten away with not being able to invert that matrix. Does that make sense? Thank you. So what happens now if things are dependent, right? Can I still get an entropy min cut, right? So before, basically, the determinism came from the fact that because they were independent, you know, I couldn't use any structure in the axis to help in the decoding. Okay? So as I said, you know, here's exhibit A in dependent sources. So Slepian Wolf. So I have so I have two sources. I have one receiver, and of course I have a min cut here. I have a min cut max flow, which is to say that I know that I can get this through, and of course the sum of these two entropies is the joint entropy of x1 and x2. So I have a min cut here, right? I mean, the most that I can get, the most that I can do, that's what Slepian Wolf tells me, is the min cut of this very degenerate network. It's a degenerate network because it has, well, here it has two sources, but it can have, of course, more sources. It has a single receiver, so it's trivially a multicast, and it has a depth of 1, right? There are no other nodes in the middle. All right? Okay, so, you know, what can I do here? And so what do we do? Well, of course, we use random methods when we teach this. And then, you know, you pick your favorite random method. You know, people use it using linear codes. Usually, you know, I use binning to teach this. But, you know, different people use different things. Okay. Let me go back to the network that I had before. And let me see if I can take the Slepian Wolf, which remember was a depth of 1, and extend it using the same sort of random arguments to an arbitrary network and get the min cut arguments. Okay, let's see if we can do it. All right. So here, by the way, I want to. So I'm just looking at multicast. So let's see. It means every single receiver here wants everything. Okay. And I want to have several sources. Obviously, if all the sources are co-located, then of course I should just, you know, press across the sources and have a single source. I mean, that's quite clear. Okay. And I'm going to use distributed random linear codes. And the main idea is the following. Rather than say, do Slepian Wolf at the beginning, get rid of all the spatial redundancy in the network, right? I'm going to add and remove redundancy inside different parts of the network depending on the available capacity and who wants what. Okay? So particularly when you look at you know, some work that is considering networks, and I do Slepian Wolf at the input to get rid of redundancy at the inputs, and then do routing or whatever I do inside the network, really what we're arguing here is, no, you know, you should keep the redundancy that you have. I mean, if redundancy in the sources was not useful, we wouldn't have mirror sites in networks, right? I mean, that's exactly the idea. In a mirror site, you put it because it's useful to you because it's closer to the receiver, and there are good reasons for that, right? And we'll see that in a minute when I look at the network cost consequences of doing this joint network source coding. Okay, so I'm going to use distributed random codes. It turns out I don't need a source entropy knowledge at interior network nodes. So the network nodes are, you know, these things are just so dumb. They just take whatever they got, randomly combine it, and just spout it out on their edges. That's all they do. Okay, so there's nothing clever at all. I'll show later that there's something clever in sort of choosing, you know, which rates to operate at from a cost perspective, right? But just from a feasibility perspective, if it's doable, every node is doing this random coding. Okay, every node is doing this random coding. Now, it turns out that if we look at this entire network, if I look at, there should only be a single A, sorry for the typo. For the special case of a single source and depth 1, right, then we get back, by doing this, the same error exponents of Chizar for Slepian Wolf coding. Right? So if you look at Chizar, right, you can find error exponents for the Slepian Wolf problem, which I just mentioned is a degenerate version of a network. It's a depth 1 network. So, yes?
It's not terribly clear, actually, the max flow min cut viewpoint of Slepian Wolf. you seem to have already made a choice as to which is the primary source and which is sort of the auxiliary source. In some sense. If you go back to the previous slide,
Yes.
I mean, a priori, the problem is you've got some joint structure on x1, x2. So how do you actually arrive at this picture, so to speak?
So what Steppenwolf is telling me is, so these are the corner points, right? But I have the whole region of Steppenwolf. Maybe I should just scribble something. So there's an eraser. I'm wearing white, so I could conceivably use my shirt, but then oh heck. Yeah. All right. Oh, but I'm wearing black on the bottom. All right. I don't know how often I run around, with a forby on the back of my shirt. Anyway, so Steppenwolf. A good thing I was wearing heels too. So okay, Steppenwolf looks like this, right? So basically, the idea is if I look at any point in my network, right, as long as the min cut exceeds this, I can get it through. As long as for each and every receiver, the min cut always exceeds this, I can get it through. That's what it's saying. So that's what the min cut is. It's an entropic min cut. Oh, thank you. Thank you, François. Okay. Thanks. It's all right. Yeah, it works too. Okay. This worked too, I have to say so. All right.
Actually, I think the clear picture would be the min cut would induce a 45-degree line. And you're saying as long as the 45-degree line, the triangle, intersect this region, then...
Right, exactly. That's exactly it, right? But basically, the idea is as long as if I look at each of these receivers, right? If I look at the joint entropy across all the sources, as long as that joint entropy falls below the minimum cut to each of these receivers, I'm okay, individually. So that's what the min cut is, okay? But instead of looking before, remember, I got away with just looking at the cardinality of the number of sources because they were independent. Now I have to look at the joint entropy of all the sources. That's what
Are you making a claim here about general networks that
yes.
the statement is true?
Yes.
Irrespective of the number of receivers and the number of transmitters.
Correct. Yeah, so that, pardon?
What do the intermediate nodes do actually?
So the intermediate nodes are doing a random code. I'll talk a little bit more in a second about it.
If I want to multicast, do you have to worry about the fan out of the intermediate nodes?
Pardon?
If you want to do multicast from multiple sources, okay,
Yeah.
do you have to worry about the overhead that if you're not careful with the fan out of the intermediate nodes?
I'll talk about the overhead in a second of
Multi-pop
determining.
case, not a single pop. In other words,
No,
we're talking about the case I go here.
Oh, no, I don't. So the only place where the degree of comes in, actually. So I'll give a sketch of the
Then you have
proof.
to choose.
Pardon? No. The only it's still a random code. The only place where the degree comes in is into the error exponent.
But the cost of if you are in a wireless and you do multicast that way, the cost, okay, can go out of hand because you have storms, right?
No. You don't have storms. You don't have storms. I realize it's very counterintuitive, but you don't. Let me show you in a second. But you don't. It really. You don't because
Where is the optimization?
The optimization I'll show you a little later, as I mentioned. Okay. So hold. But for the time being, let me assume that you gave me the network and you simply asked, not so much how can I do it most cheaply, which I will get to, okay? But what I've asked is, can I do it? Given that you're going to use these links, now maybe you could have gone away with far fewer links, right? That's a different problem.
So in the model you have talked up to now, just to understand,
I give you the network.
node says to everybody that you can do, right? No?
Each node is going to send on each of these edges, and those edges have no cost at the present
So
time.
each intermediate node says to all of its outgoing edges.
Sends to all of the outgoing edges, but it can send a different combination to different edges.
Conditions can change.
I understand that. Yeah.
Right. Okay. Correct.
The second bullet mean redundancy is removed.
So the redundancy is removed and added, meaning that it doesn't mean that you generally, so what happens is that naturally what's going to occur is that sometimes across a cut, right, you will see redundancy in data spatially, and other times you will see that you're actually combining data at a node, right, and removing redundancy. Okay, so it's not something where you're doing it all at the source, sort of removing all the spatial redundancy and then network coding. Well, I'll show you in a second the lack of separation.
That's what's hiding the Slepian-Wolf scheme, right?
That's what's hiding the, exactly.
You're going to describe that? Or?
Yeah, I'm going to talk to you. Okay. So I'm going to talk about the cost, which is a very good point, right? But right now there's no cost, right? I give you these links and you're going to use them. Maybe it was a stupid idea to use these links as a separate matter, right? Yes, David.
But the correlated source is not an arbitrary correlated source, right? It's a correlated source on a finite field, right? Let's
yes,
look at the sources.
That is
it's
correct.
on a finite field.
They are on a finite field.
So essentially what you're saying is that if I want to do distributed source coding, I could use linear code. Just like what Gallagher tells us, that you can use linear to do.
Absolutely, yeah, actually goes all the way back to Elias.
And you're shifting the linear codes to the network.
Correct. That's exactly it. That is exactly it. Right. Actually, now that I spent a long time, you know what? I'm going to punt the outline because otherwise I won't end at noon. And I know that speakers who eat into lunch are themselves eaten. But basically, the way we do it is we use a method of time. So very similar to what Chizard does. The only little extra trick, if you will, and this goes back to the question of what do the nodes do, is you need to have a little extra step to bound the probability at a node of mapping to a zero. Right, so remember we had this problem that we just trying to avoid zeros before. Okay, so that's the extra little step that you have here. So in effect, if you look at the error exponent, you compare it to the Chizard error exponent, everything's the same, except that there's an extra term which depends on the depth of the network, right? Because the depth of the network is the number of times that you could screw up, right? By hitting a zero when you shouldn't have. Okay? Now, so basically what this is saying is my random codes generalize Slepian-Wolf to an arbitrary network. Okay? Arbitrary number of sources, arbitrary number of receivers, as long as I have multicast and everybody wants everything. Everything's linear, everything's random, everything's lovely, everything's distributed, right? All the coefficients are chosen in a distributed way. And now, here comes the question, why do I care, right? I mean, okay, so, you know, we do these sometimes because we like it, but, you know, would anybody in networking actually care? And here's a little example, and this gets back to John's point. So, suppose I have two sources here, and if the sources, if the sum of the rates on these for these links is, so suppose that I'm going to have two sources, and I'm going to pretend I have a virtual super source, because remember, for multicast having one source or several sources, it doesn't matter, right? I'm going to just put a big super source at the beginning. It doesn't change anything. Okay, so suppose that I have a big super source here. What happens is that, in effect, if I consider a super source that's feeding these two actual sources, if the sum of the rates going from the super source to these individual local sources, right, is R, is the rates that's requested at the receivers, then, you know, it's basically I'm going back to the original case where they're independent. Okay? Or maybe if the super source wasn't independent, I was able to make it independent. There's nothing to be had. What's interesting, right, is when somehow there's overlap between these sources, right? They're not separate. So here's a little example. This is the butterfly example from Alsvedera. And I have these two sources, these two receivers, and the two receivers want what's available at both sources. And what happens here is, I'm not going to go in detail because time runs on, but the triples that I show here are, this is the physical number of degrees of freedom that I send. These are the degrees of freedom that accrue to receiver 1, and these are the degrees of freedom that accrue to receiver 2. Okay? So for instance here, I have 2 degrees of freedom, maybe, and they're both helping receiver 1, but they're not helping receiver 2 at all. If I look down the middle here, I have 1 degree of freedom, and that degree of freedom is going to benefit both receiver 1 and receiver 2. And by the way, this is exactly the way you represent things in order to use network coding for optimization. So I mentioned briefly that, of course, this allows me to go away from trees, and in particular Steiner trees, which is what we usually use in routing for multicast. It turns out that you can use this for doing the optimization, and what it's really doing is it's taking directed packing of Steiner trees and removing the integrality constraints that make the Steiner trees hard in the first place. And then what you have is just a convex optimization problem, and you can solve it actually in a distributed manner, but certainly in polynomial time. Okay? So that's what we have. And so here what happens is, if I do a joint network and source coding with this random approach, the cost of transmitting, suppose that each link has a cost of 1 per physical degree of freedom, because I pay for physical degrees of freedom sent. Okay? Then the joint cost here is 9. If instead what I had done was remove at the sources the overlap, right? That's to say I would have done Slepian-Wolf at the sources, and here by symmetry there's no reason to keep more on one side than on the other, right? So basically I'm working sort of right here in the middle of this dominant face of the Slepian-Wolf. Then if I had removed basically removed almost all overlap at the sources, and then done network coding, I would have had a separate cost of 10.5. And that goes to your question that I can use fewer resources. Okay? So basically, at this point, you say, okay, well, random has held us in very good stead.
Are you doing?
Yes.
Are you doing broadcast or multicast? Does everybody wants to get everything?
No, just the 2 terminals.
No. In general, if I have m sources,
Yes.
the population of receiver, let's call them ZM for each source, is a subset of all the nodes. That's
Correct. It is a subset, yes. Absolutely. Just like here, only the bottom ones want the stuff. Oh, David.
But in terms of the solvability condition,
Right.
it's the same, right? Whether you do source
It's the same one. It's the same one. So the issue here is just that I can choose a subgraph with less capacity. Right, overall. I can choose a subgraph.
In terms of the use of the bottleneck resource is the same, right? Because
it depends. It depends. Actually, it depends. It really depends. Here I'm looking at a.
So you've changed the metric, right? When you talk about cost, you've changed the metric.
I've changed. So what I'm saying is the reason this is interesting is if you gave me the network, like starting with the question John had before, if you gave me the network and just said, this is the network, can you do it? The answer is yes. And the next question is, what could you do with a cheaper network? Right? I mean, that's the next question. That's the duh question, right? It's like, well,
But you cannot do it with a network with smaller min cut.
You cannot do it with a network with smaller min cut.
So that's what I meant by bottleneck resource.
Oh, I see. Yeah, that's right. That's right. Okay, so what next? All right, so what this says is the dependence among the sources doesn't hurt us. I can still do this distributed random coding. Now there's a caveat. When I had independent sources, the decoding was easy, right? I just needed to do matrix inversion. Now it's not so good because, even let's go back to the Slepian-Wolf. If I do a random linear code, the decoding may be difficult. Depending on the structure of the correlation among the sources, the decoding may be difficult. So I may have to do minimum entropy decoding, which would be awful, but, for a feasibility question, it doesn't matter, right? Of course, I might be able to add some structure. Maybe I can add a little error like the stuff Michelle and Todd Coleman and I had done. But going back to my comment before about mirror sites, if I'm designing the correlation at the sources, for instance, if I'm designing where I put mirror sites, what this is saying is instead of having full copies, right, I may just have coded versions. And of course, I can choose those coded versions to be linear, and then the decoding is easy, right? It goes back to linear decoding. Make sense? Okay, and so you can set up a whole optimization question. Actually, we just had a paper at this last ITW last week in Cairo with Aditya Ramamurthy on doing this optimization for placing mirror sites. And of course, it's particularly interesting, I think, from an application point of view, because the main application where network coding has sort of gone into is peer-to-peer networks and mirror sites, things like UUC in China and so on. Okay, so what next? Okay, so we were able to put in correlation, and we found out that, you know, the min cut max slow approach still holds, and it does beautifully. Okay? But we still had perfect channels. So what happens when the channels are not perfect? Well, let me start out with erasures, right? Because erasures are easier. And this is an example taken, you know, straight out of Dick Blayhood's book. So you have, you know, 3 nodes, and you have an erasure channel going from A to B, an erasure channel going from B to C. So, of course, if I just do end-to-end erasure coding, like, you know, something like, say, a fountains code type of approach, then the capacity is going to be really the probability that it'll get lost here or there, which is the product of the 1 minus epsilons. If instead I do, you know, a min cut approach, I say, well, the min cut approach is just the min of the 1 minus epsilons. And the way one traditionally does that is you would say, oh, I know how to do this. I'm going to do a erasure code at A. I'm going to decode it at B. Then I'm going to re-encode at B. And then I'm going to decode it at C. Right? Now, of course, the problem is if I go to a network, right, here is a daisy chain, but if I go to a general network, I may not be able to decode in the middle. Right? Because, you know, I may have nodes that just don't have enough degrees of freedom to decode. So it turns out that if I use network coding, the minimum cut is the capacity. And for erasures, correlated or not, as long as I have, you know, just general algoritmicity conditions, just looking at average flows, then the min cut is the capacity. And basically what you're doing is you're doing random coding again, but you're doing it in time. So the nodes are storing received packets in memory, and they're just mixing everything that they ever saw, and they're just pushing that out. That's it. That's what you're doing. Every node is doing that. There's no decoding in the middle at all. Even here, I can get away with just no decoding. So every packet is just randomly mixing whatever it sees, and it just plops that out. Okay? So you're just doing random linear combinations of memory content sent out. You can use this in a block fashion. You can use this in a rateless fashion. And actually, one of the things that you can do is suppose that I had Poisson arrival, so that's harkening back to the previous talk. Let's just assume memorylessness everywhere. It turns out that you can find, you can generalize the expression from Jackson networks for, you know, product expression, but instead of having a product expression in terms of packets, you have a product expression in terms of innovative packets, which are new degrees of freedom across a cut. Okay? So you can actually, this was joint work with Desmond Munn. You can actually find out at each and every node the product, you know, over the entire network, a product expression for the number of degrees of freedom residing there. Does that make sense?
How much memory you need?
Pardon?
How much memory you need?
So that's a very good point. In this case, we're showing, because there is no feedback, there is a memory that is infinite or of the size of a block that you use, and you can find error exponents with the blocks to give you some idea of how the error goes with the memory. I'm not going to talk about it. Maybe I'll talk about it at the very end if I have time. If you have feedback, then the amount of memory that you need is only corresponding to the number of degrees of freedom that are still missing, the maximum number of degrees of freedom that are still missing at any node downstream from you. Okay? Because basically what you can do is you really think of subspaces. So what you have, you don't need to keep track of everything. You just need to keep track of the coset space of what everybody saw.
And you can do that.
Mm-hmm. Yeah. And actually, that's the theoretical underpinning for TCP with network coding. So the stuff that we showed at Infocom, that's actually the theoretical underpinning for the ACS, is the subspace. It's simplified, of course, but that's what makes it work well. So I'm going to skip some things, but basically what happens now is, a similar result was also obtained by Dana et al. And Baba Kasibi, but basically what they were doing is they were assuming that each and every link, that you had side information of what erasure happened everywhere. But we don't need that, because remember, at the end, all I'm going to do is just invert, right? And since all I'm going to do at the receiver is just invert, I don't need to find out the sad story of what happened to what packet where. All I need to do is each packet carries with itself a header, which is in effect just a canonical basis right? Originally the packets, first packet is 1000, second packet is 010, and so on and so forth. And as this traverses the network, that header, which is transformed algebraically in the same way as the rest of the data, right? So a packet is really a set, it is a whole vector of symbols, and the header is just saying for each of these symbols, how are you combining them symbol-wise among packets? Okay? So you just put a header, and that header says, well, I am a packet that represents a vector of this many symbols where the following different combinations occurred. It just goes to the network. So you don't need to keep track of the sad story of who did what to whom. Okay? So I'm just going to punt these two. Okay. So the main thing is erasures can be handled readily. So erasures are not a problem. And by the way, not only are they not a problem, but we have a very good handle on, error exponents, queuing type stuff, generalization of queuing type stuff to now degrees of freedom. So now the question is, well, what about errors? Right? Erasures were nice because remember, I can still invert everything at the receiver. That's how I decode. Errors are more complicated. There's a lovely set of results. One was a more restricted set of results shown by Shashi Bharati, and then a more general set of results shown by Young and his collaborators, Raymond Young and his collaborators, that if you have the multicast again, yes?
Cutting this header around, isn't it a little bit propagating the information about the network? That's what the CB does, right?
That's a very good point. So there is a whole literature, and actually I think probably the main work in that area is done by Christina Fraguli, but there was also work done by Tracy Ho with Nick Harvey, and this is also done now Athena Marco Polo. So there's a whole area on network tomography with network coding. I'm not going to talk about that at all, right? But basically, right now, I'm only concentrating on feasibility and the fact that the header is telling me how to decode. The headers, when I put all the headers together, they give me the matrix M, and then I invert that matrix. Okay, but you're right, there are applications. Okay, so it turns out that even if I have errors, I have basically a separation between the link coding and the network coding. Right, so that at each link, I could operate it in an error-free way, and then I just network code over the whole darn thing, if everything's point-to-point. Again, we're going to have random approaches because the min-cut max flow bounds hold. Okay, because the min-cut max flow bounds hold. I don't have the same detailed, sort of fine-grained representation of what's going on in behavior as I did with the erasures because, it's errors, but the whole thing holds. Now the next question, of course, is the point-to-point assumption crucial? And here I'm going to talk about some of the stuff that David and his collaborators, Vestamer and Suhas Gavi, have done recently. So I'm just going to talk about some of these recent results. So what happens, for instance, in the case where I have interference as a dominating factor, for instance, at high SNR. To borrow from David's work, you're kind of approximating the multiple access region roughly in this way, and you have one part here, which is where you model the errors, the links as error-free links, and you have another part here in red, where you're modeling it, in effect, as an additive channel over a finite field. So I'm taking the same pictures we had before without the exogenous inputs, and instead of having an arbitrary linear function here, you're having an addition. Right? But you can see that this, it has a similar feel, right? You're using these linear codes. The only difference here is that part of the linear code is given to you by the network, by the physical characteristics of the network. And so, not surprisingly, they get a very nice min-cut max flow type of results. If you look at high SNR regime, so this is it's high SNR, but it's a high gain. If you instead you look at fixing the gain, but actually pumping up the energy, we have some recent results with Ivana Merritt and Andrea Goldsmith, where we showed that the analog network coding actually, again, for the multicast, is near optimal. Okay? But in all of these cases, what I'm trying to say is, whether you go back to something like this, which is determinist, which you're looking at finite fields, and therefore, you have, a coding approach, a network coding approach, or whether you look at something which remains analog, is that in all of these cases, you have min-cut max flow and random arguments hold. Okay?
Does it mean analog?
Pardon? Analog network coding means that you're using the interference as a code. Using the interference as a code. Okay?
So is this example here?
No, this is actually taken, I'm approximating very roughly the work of David, where this actually they first make a discrete approximation.
Right.
So to a finite field. Whereas here you don't do an approximation. You remain in the complex domain here. So I'm just putting this to say that it's not just all because of finite fields. Okay. Okay. Beyond multicast, 1 minute. Beyond multicast, solutions are no longer easy. Okay. Even in the scalar linear case, you just don't know what happens. And actually, I'm hoping to contribute a problem to the open problem session. So what happens is that it no longer suffices to avoid roots. It's just the way it is. Okay. And therefore, I'm not going to be able to just get away with, pretty much anything because I'm just, because it's multicast or sons of multicast, right? And therefore everybody wants everything. So I'm not going to talk about equivalence. I'm just going to say the following. Sorry, I just had more questions, which is wonderful. I just had more questions than I expected, so I'm a little behind. Pardon?
Let's get one of the good stuff.
Well, the other stuff was good too.
That was not newish.
Pardon? The other stuff wasn't newish. The other stuff is really new, yeah. But some of the stuff is new too. Okay. So the conclusions are the random approaches seem to hold us in very good stead for multicast systems under a variety of settings. General networks, correlated sources, erasures, errors, interference. It really seems to, it does very well. For more general network connections, okay, the difficulty arises even in the absence of channel complications. I don't need to add errors for things not to work well, right? Basically, linear doesn't suffice. Okay, obviously, even linear doesn't suffice, and the examples that show that linear does not suffice actually are borrowed from a toroidal theory. And so there are open questions even just about, so there's a lot of work right now about the possible matroidal nature of network coding problems. And certainly for some network coding problems, there's been a lot of work in particular by Doherty, Freeling, and Ziegler on showing that. What we can have that is equivalences between networks. So one of the things that I didn't show, or that I didn't put forward, but we showed recently with Rolf and Michel Lefros, is that if you have a network with point-to-point links, even though we don't know the capacity region for arbitrary connections of that network, even though we don't know that capacity region, we know that it's the same as if those links were error-free. But the problem is that I can no longer do my old tricks. What was my old trick along all of these min, cut, max, flow? Is to say, hey, min, cut, max, flow is an upper bound, and then I show that I can achieve the upper bound. Right? So it's always an achievability. You're always showing feasibility of an upper bound. The upper bound is min, cut, max, flow, and you show achievability. In general, I can't do that because the min, cut, max, flow, of course, is always an upper bound, but I know it's a loose upper bound. So I can't choose achievability. As a matter of fact, I don't even know what the rate region is, okay, for general networks. So I don't even know what the rate region is. All I can tell you is that if I only have point-to-point, right, I can reduce every link to being error-free, which basically is saying that there is a theoretical underpinning for layering inside of point-to-point systems, not point-to-multipoint systems in terms of the edges, okay? And the questions here is, so my big question here is, okay, what can I do, right? It seems like, first of all, there are probably a ton of other problems in the min, cut, max, flow setting where I should be able to, use random codes. Different versions, right? But I should be able to get a lot of stuff. Can I do that, and then can I still consider more general networks by breaking up large networks into small, reasonable pieces that make sense? Okay. So the thing that I like to, the comment I like to conclude with is, if you look at people, for instance, that do devices and people who do circuits, they've really figured out how to model devices, how to do some sort of granularity to model devices, and then to put the whole circuit together, right? And the whole circuit, in general, is a mess, right? But they have means of doing it, right? They have SPICE right? And can we do something similar? Can we do something where we chop things up so that we sort of stick the randomness at the micro level in the right spot, right? Which is what people in circuits do, right? That's really where they consider the noise and all that junk, right? And at the macro level, okay, it's going to be a combinatorial mess, but in this way, it's neither our fault or maybe our problem. Maybe it's a problem, but it's a separate issue. So to separate where we can really make use of the randomness, right, and where we really have to deal with things combinatorially. And that's it. I'm sorry for going over and not managing questions that came up.
We didn't go over because we started 5 minutes.
Oh, we started 5 minutes. Oh, so I did go over. I was preternaturally well timed. I don't know if we should.
We have time for questions. Let's take a few questions.
David.
How easy is it to add and remove nodes from a multi-class group dynamically? And also, how easy is it to set up and take down multi-class groups online?
So that's a good. Let me repeat the question in my loud voice, just in case people didn't hear. So the question is about roughly. Let me rephrase it. It's roughly about dynamic multicast groups. Okay? So one of the things clear is if somebody leaves a multicast group, right, it doesn't affect the others. And if somebody joins a multicast group, if my field size was large enough to start out with, as long as the min cut max flow is satisfied for that member who joins, I'm okay, right? Now, that assumes that I have a particular network. Now, going back to the issue of the cost, right? It may have been that I set up my network in such a way that the cost was the best for a certain set of receivers, right? And it may be that I may not have my network set up in such a way that had another receiver joined, I would have selected that subgraph. Now, one of the things that you can do, I mentioned that the optimization now becomes a convex optimization. One of the things that you can do is if you have a stochastic model for how nodes are likely to come in, right, then you can actually set the problem up as a dynamic program where I'm sort of optimizing my cost right now, knowing, for some sort of future, right, knowing the expected cost because of things that may be coming in. And I'm not sure we've done some work on that. So we can talk a little bit more, but that's the broad answer. But in terms of if just you have the network, then coming in and out, it doesn't matter.
What if an entire new multi-class group had to be set up?
So the question then becomes: so if you're saying entirely new, are they receiving the same stuff as the original ones or not?
No, an entirely new source.
An entirely new source. Okay.
Entirely new multi-class group.
So I haven't gone into that. So in general, right, if I don't have a true multicast where everybody wants everything, the general problem is hard, as I just sort of alluded to briefly. What often happens, but going back, there is an optimization statement which is guaranteed to always do better than any routing. That is to say that for any combination of multicast, unicast, and so on, you know that it will always do better than routing with coding, with a random code. And what it does is that it completes locally to multicasts. The problem is the following: it's NP complete. And the reason it's NP complete, the portion of that problem makes it NP complete, is to decide whom to mix at different nodes. Okay? So once you've decided to mix, if you restrict yourself to decoding only at the receiver, which by the way may not be optimal, but is guaranteed to always do better than not coding, or at least as well as not coding, right? You can still use a random code, you're locally completing to multicasts. The problem, the difficulty of the problem, and you can show that to take it back to standard trees, is that whom do you mix, right? Because once two things are mixed, then they remain mixed downstream until they get to the receiver. I don't know if that answered your question.
I think
Okay.
I understand it better.
All right.
So for time, is it correct to say that for time varying problems, we have a peak of lithium sneaking in or not?
I'm sorry? Could you
For
repeat?
time varying problems, whether the graph is time varying or the groups are time varying or the errors are time varying, we get into a peak of lithium or not?
Into NP completeness? No. So the time varying, for instance, with erasures, that's not a problem.
Because all of these
Oh, no. Let me go back. If the number of receivers or senders changes, that does not matter.
No, the graph. I mean.
If you're trying to design a graph,
I'm not trying to design a graph. The graph is changing like you will in mobile wireless.
correct?
Then
So I tried to, okay, it's not that simple. So I tried to make a taxonomy, and maybe I've gone over it too quickly. If you still have a multicast system, right, and you're looking at feasibility, there's no incompleteness. Everything that I just said holds.
if the graph is fixed.
No, if the graph is mobile, but it's just like the erasures. All I care about is that the average multicast holds. Okay? That's what I was trying to convey here. All I care about is that the average multicast holds.
Which means?
Which means that the average mean cut, if the mean cut that I saw over the period of time that I was transmitting, okay, exceeds the rate that I tried to send, my random coding will suffice. Okay? If I'm trying to optimize the graph that I use over any time varying thing, then I have a dynamic programming problem, which in general may be very complex, if I'm trying to optimize the graph. But if I'm simply trying to transmit, I know that my random coding holds as no MP completeness.
How do you measure cost here exactly?
You can measure it however you wish. In general, it has to be a convex function of.
No, in reality, what do you call cost?
We've looked at several things, and people have looked at several things. So some of the costs are linear costs with transmission. That's to say that it's how much traffic do you send through. We've looked at costs in terms of energy. Actually, in wireless systems, when we have a hypergraph, right, because of the intrinsic wireless multicast, physical multicast. And then we've looked at energy. There's some very interesting things actually looking at cost in terms of delay. I really didn't show the optimization, but you can take a slightly different version of that optimization to look at minimization of delay. That's what people, for instance, Yunan Wu at Microsoft has taken our optimization and looked at it for minimizing cost for peer-to-peer downloads. Okay, so people have looked at different versions of cost. Okay, from linear cost to just convex cost. There's also been work, for instance, by Edmund Ye looking at taking kind of an MM1Q type cost of congestion and applying that within our optimization framework. For instance. People have also looked instead of utility maximization, right? There's been work in that where you look at utility maximization, which is of course concave utility versus convex cost. So there's been a lot of different approaches.
Okay. Perhaps in the interest of leaving time for lunch, maybe we can continue the
discussion.
Yes,
please catch me later. Thank you.